Hey everybody, in this video we are going to go over graphing with transformations, and we are working on the absolute value of x. I like to say absolute value of x because really you could take the absolute value of any function, and the way it works is as follows. I'll demonstrate with taking the absolute value of x. So in the previous video we graphed the line y equals x, which is a linear function. It's the parent of all linear functions. It is also known as the identity function. So a linear equation will look something like this right over here. When you take the absolute value, if you look at the equation carefully, you'll see that it's y equals the absolute value of x. That means y equals positive. So if the y is positive, I'm going to take every location where the y is negative, which is here below the origin. That's the negative y-axis. And all I'm going to do is I'm going to reflect it over the x-axis. I'm going to reflect it up. So what happens is you end up getting a graph that looks like a V. There you go. So this is the parent function, so I'll quickly sketch that in a moment. The slope here is 1, and the slope here would, of course, logically become -1. When I have a transformation of the absolute value graph, a few things can happen. A negative as negative in front for the A value, right? A negative A value will cause what we call a vertical reflection, so it's going to flip that in the vertical direction. -3, hopefully you remember in the previous video, I'll flash it on the screen in a moment, but -3 moves our graph horizontally, so to the right 3 units, and then +6 moves your graph up 6 units. When I'm graphing it, I tend to reorient or recenter or calibrate myself to center around where I am shifted, the point HK, and I draw a little crosshair right there, and then I do any other stretching or reflecting or compressing over that point. So in a nutshell, there it is. As for symmetry, we're going to see that this is what we call even symmetry. Even symmetry is where if you fold it over the x-axis, that it is a mirror image, so like a butterfly kind of thing. It's called even symmetry, and I'll write down for you that it basically means when you plug in an x value that you will get the same output that you would get if you plugged in the opposite x value. So a positive and a negative x will both give the same output or the same y value. So let's get into it. So just to look at y equals x, absolute value of x rather, with the, again, I'm going to ignore the b for now, but with a, h, and k as a parent function, y equals, we'll have a 1 in front, absolute value x minus 0 plus 0. So that moved it 0 units to the right, 0 units up, and the 1 means it has the standard default slope on each of the 2 branches coming out from the vertex right over there. So where are they coming from? They're coming from this point right there. The end behavior for something like this is, well, to use limit vocabulary, the limit as x approaches positive infinity is, that's asking you what is the y value doing? Well, to the right, as we go to the right, we're going up to positive infinity. And then if we fill in negative infinity, because of this even symmetry, negative infinity absolute value is also positive infinity. So it's up and up. So it's going to behave a lot like a parabola or other functions of that nature. The domain, this goes to the left forever and to the right forever. The domain is talking about x, so left, right, any gaps, any breaks? Nope. So the domain is parentheses for values we can never actually reach. So negative infinity, comma, that's where we start, and we end positive infinity. As for the range, that is not going to be negative infinity to infinity, or in other words, all real numbers. The range from bottom to top begins at, in this case, 0. We use a square bracket because that indicates that 0 is included. A parenthesis means we can't include that. Comma, and it goes up forever until positive infinity. The symmetry, as I said for you before, is what we call even, and that would mean f of x and f of negative x, or the opposite of x, are equivalent. The output, f of something, is a y value. When you plug in an x, is equivalent to plugging in the opposite x. There you go. So let's get into the next example. So the first one we see with transformations right here, what is it asking us to do? Well, we are moving to the right 3, up 6, and that right there is A, A is less than 0. In other words, A is negative. That means we have a vertical CAL at the end, guys. That's all spelled out correctly. Let me block this off since it's blending. Vertical reflection, like I did with the little paper graph at the beginning. So let's dive in. Right 3, 1, 2, 3, up 6, 2, 3, 4, 5, 6. So I am calibrated to that spot. That is like my new origin. And that point right there is that point right there, okay? That's the point getting me started. That is my, for vocab purposes, that is my vertex. And this vertex is called a node. It's a node when they meet at a point like that versus, let me just show you over here, that we would call a cusp. So if you wanted some vocab words, if you take calc in the future, that's cusp, that's a node. But in either case, it's the vertex. Okay, now the negative just flipped it over. So down 1 over 1 is still my default to use for graphing. Nothing special going on. No stretches, compressions, or any of that good stuff. There we go. Arrows on the end. Some graphs don't have arrows on both ends. This one does. There we go. That is our first 2 examples of absolute value. All right, let's move it a little quicker. I want to be under 10 minutes for this. So the next, moving my markers, the next 2 examples are right over here. So let's write out what are our transformations. So on the inside, where are we going? Right 5. Where else are we going? Down 4. That right there is a vertical stretch of 3. Vertical stretch of 3. Vertically, we're stretching by 3. So let's calibrate our center. So where am I going? Right 5 and down 4. Right 5. 1, 2, 3, 4, 5. And down 1, 2, 3, 4. So my new origin, my new place to be centered at, center my screen around, is that point right over there. That means that is where my vertex is. Then from here, the 3 out front, vertical stretch. So instead of up 1 over 1, I'm going up 3, out 1, up 3 over 1. Just mimicking the original parent function and applying a vertical stretch to my graph. Oh, sorry. Go through the points. Don't be sloppy like me. My vertex is at the ordered pair, x, comma, y. There's my vertex, and there we go. All right, sorry, pretend I passed through those points, a little sloppy. 1 more, we are doing great. Here, where am I moving? Left 2, down 1, left 2, down 1. That is my new center of the universe. That's my origin right there. That is -2, -1 right there. Now, I have 2 things happening. This is when, if you're being asked by your teacher to list the transformations, if you have a -6/5, you want to say 2 things. The negative is one aspect of it, and the 6/5 being 6/5 instead of being 1 is another thing. So what is that? Over here. So when A is negative right here, A is negative, that's a vertical reflection. That's one thing. Then it can be one of these 2 things. In this case, 6/5 is greater than 1, so that would mean it's technically a vertical stretch. 6/5 is 1 and 1/5 if you want to think of it that way, or 1.2 if you want to think of it that way. So again, everything's on here. So what's a vertical stretch look like when A is greater than 1? The graph will become vertically stretched as opposed to a vertical compression, which would squash down like that. Everything will push towards your origin, or depending how you graph, your new origin, if you will. All right, so now that we've addressed that. Down, now, like I talked about in the linear one, we could go down 6/5 out 1, down 6/5 out 1, but because it's essentially a line, steady, we could save our time and our brain energy. 3, 4, 5, 6 down, down 6. And then we go out 2, 4, 5. Because that's the same as going down 6 and out 5 times. Done. Now, just quickly to address domain and range, while I have, I'm already over 10 minutes, but let's try to keep it under 11. Domain for this one, the domain is still from left to right going on forever, negative infinity to infinity. However, I just want to show the difference in the range. The range from bottom to top, the bottom is going from negative infinity at the bottom. It goes down forever, comma, until what is the biggest y value we hit? -1. Bracket, because we actually hit it. So the range goes from negative infinity until the highest y value of -1. We can call this a maximum, okay? It's the highest point, and then we can call, say, this one a minimum. It is the lowest point. In both cases, we can call them absolute max and absolute min. That means it's overall the highest, lowest point on the entire graph. If you feel like you can transform an absolute value function now, great. Thumbs up. Comments, questions, concern, type away. Help each other answer somebody else's question. And the next one I'll be doing is a quadratic equation, which the graph is called the graph is called a parabola. So adios, thumbs up, comment, something, bye.